So my role is to work with our partners like Scott in the Northeast. So I cover everything from Eastern Pennsylvania all the way up to Maine, all of New York State. In particular, I focus on education. So I visited most of the institutions in the Northeast over the last year. A lot of them, I can honestly say, are not up to snuff first compared to here at Bergen. At the you call it the open space? What do you call that?
STEM Research Center.
STEM Research Center. Okay. Typically, people have open spaces. That's far and above a lot better than I've seen at most places I've visited. So you guys are pretty lucky.
Can you say that again a little louder?
Far and above. Right? And you ask, well, why do you have a space? Why do you have a space like that? Right. The reason you have a space like that is to prepare you and the professors, help the professors prepare you for the real world once you get out of these four walls, right? That's the goal. And that's a main theme within Tektronix and Keithley. Just to inform you, Tektronix, they focus on things like spectrum analyzers, oscilloscopes. Keithley focuses on things like DMMs and source meters, which I'll explain in a little bit, as well as switching electronic signals. That's their main forte. So basically to test semiconductor devices. So I have a little short presentation here in terms of why we do what we do, where we focus to help you and the industry with the latest technologies and manufacture and test and research with the latest technologies. Okay, so one area is 3D sensing. 3D sensing is everywhere, right? Sensors in general are everywhere. If you have an electronic device, whether it's a phone, there's sensors, there's a ton of sensors in here, there's wireless in here, which I'll get into. And the market is just going up and up and up for 3D sensors. We sell a lot of Keithley products testing these sensors, these diodes, as it were, lasers. The lasers that go in these iPhones are tested by Keithley products around the world. And these are some of the manufacturers that make these things, right? And these typical applications are face recognition, right? You get that with the new phones, LiDAR mapping. So LiDAR is laser radar, right? In automobiles, there's now laser radar systems, for example, as well as traditional radar systems. VR gaming, right? So the VR gaming has to sense where you are and have the feedback fast enough in the game so you're not getting dizzy. Right? There's a lot of latency, then you're going to get dizzy and fall over. Right? That's key. Right? A lot of medical applications, remote devices that go in your body. Right? That has to be tested to the nth degree. It's really, really important. In automobile headlights, there's a lot of technology just in the headlights, LEDs, for example. So in terms of how big of a market is this, right? So it shows you $20 billion revenue on these LEDs. They're so pervasive everywhere in the world that and there's huge growth. This just breaks down what industries they are. But you can see, and it's only going to go up. So the demand to make sure that these devices work the first time is really important. So a lot of the applications are general lighting, automobile lighting, aircraft lighting. They're all going LED, all the lighting. On the street lighting, everything. So, automobile is a great example of where everything comes together. You got radar, you have high-speed communication, you have lighting, you have sensors everywhere in the car, right? So a lot of this, there's a big focus in the Tektronix on being able to test every device that goes into a car. You can imagine in the engine, it's very hot and cold temperatures these devices have to be tested to. So they have to test them over a wide variety, as well as battery technology. As you can, I think in your STEM research, you're doing some converting a motorcycle to
a car.
In a car, right? So that's a big focus. There's a lot of universities I visited that have competitive electronic vehicle teams, which we've actually helped out donating equipment so they can test their batteries. Right? So one of the items I brought is a battery simulator over here.
pointing at.
Oh, sorry. I thought.
Battery simulator, which basically simulates a battery. So instead of having to rely on a store-bought battery to test your device, see how your device performs with the battery, there's a lot of errors in batteries. So we have a simulator to be able to test those out. I'll talk about it. Medical technologies, as I mentioned, I mean, there's everything from your body's your pulse, your heart rate, all plugged into your cell phone. That's a very large market. You got your electronic watches, monitoring watches. You can do your EKG now, and there's a whole host of things. And these are a lot of customers we work with to provide those things, and you just see the growth. So there's everything you're studying here is going to have real-world applications when you leave this place. And it's pretty large, very large markets that you can go to. So this is sort of connected devices. Right? What do I mean by that? There's something called Internet of Things. Everything is connected now. We sell to companies that make mattresses that are connected to your phone. That can you can program it to, I think it's called 8. Ever hear of 8 mattress? They have water channels in the mattress that can regulate the temperature of the mattress. And you can program it with your phone, right? And it'll respond to your body temperature. So there's sensors in the mattress to keep you cool or warm, depending on the time of year, and it will actively respond to your body. That's an example of Internet of Things, right? Mattresses. I visited Amazon Robotics. So you have these very large, near New Jersey Turnpike, very large buildings. You ever notice how many cars there are on the parking lot? Not too many. They have these robots that are about this size that go around picking up all the racks of products and taking them where they need to go. And then the humans actually pack them up in boxes. So it's pretty amazing. And there's a whole company that builds these robots for Amazon, and it's an Amazon company. Very interesting. Again, Internet of Things. They got to talk to each other when they're in this warehouse. Yeah.
Where is that building located?
It's off the New Jersey Turnpike. What exit is it? It's got, that? There's like a Wayfair. There's an Amazon.
8A.
Is it 8A? Yeah. It's in between Philly Turnpike and New York, somewhere in between there.
Road.
You'll see it.
Center, Jersey.
It's on the west side of the highway. It's pretty impressive. But Amazon Robotics is up in the Boston area. Tablets, smartphones, PCs. I mean, look at this PC. That's the least of it, right? All this other stuff is up here. Smart TVs. I mean, it's just pervasive. So this is sort of a good example of an ecosystem of connected devices, right? Based on general themes, and if it's private, hospital, government, and then breaking it down into exactly what it is, where its uses are. So it's a very large ecosystem for these devices. So what's driving these industries? Okay, costs are going down. Costs are going down, and customers aren't going to pay more for more technology, right? I mean, except for the iPhone, which price seems to keep going up and up and up. Most technologies, they're packing better performance for a lower cost, for a bit or gigabit or what have you, or whatever the unit you use. And also modularity is increasing. They're packing more and more of these various devices into one device. And it's just an example of a phone, right? If you think back, well, you probably don't know this, some of the younger people, before the phone just used to be a phone. It wasn't a camera, right? You couldn't connect to the internet, right? It didn't have any sensors, it didn't vibrate. There's so much packed into this small device. So modularity you keep. And what's even more difficult that requires test equipment such as these that I have here is you need to be able to test everything on that board, right? So you have RF, you have digital, you have analog, motion. I mean, there's temperature over a wide variety of temperatures. So they all have to work together and not interact negatively with each other in the device over temperature, the life of the product, right? It's got to work, especially in military applications. It just has to work. That's one reason that why in the military there's very old systems, because they don't like to change. They know it works, and we support 20-year-old oscilloscopes, for example, on the Tektronix side, for the military, because it takes too much to change. They know it works, and they just have it's got to be, just communicate with the satellite, for example, and they can't put the time and effort in to change things. So there's a few key things for design challenges. As I mentioned, you're integrating your wireless, digital design, max and battery. Battery life is key, right? The longer the battery life, the better. The less power consumption that the battery draws, things of that. EMI and EMC pre-compliance. I'll talk about that in a second. Wireless standards pre-compliance. Wireless standards, they're making the wireless language, if you will. We call 802.11. They're coming out with more and more flavors of that. There's 5G stuff, for example. That's just an example of one flavor. They're just adding capacity, be able to transmit more data over wireless in smaller devices under lower power. It's like everything is competing. They want it faster, lower, cheaper, right? To be able to test those things is very difficult. And then interference of things. With so many things, like our phones can't interfere. I have to make a phone call. You have to make a phone at the same time with your phone, right? There's so many things competing. And I'll have a little video. It's actually a good segue. Sorry, I should have had this. I'll pull it up later. I can't find it right now. So this is a typical block diagram of what you might find on an Internet of Things device. Right? So you have wireless device here. You got power regulation here. You have a microcontroller here. You got software running the microcontroller. You have inputs and outputs. Right? One key thing with any device is it's got to be compatible with the outside world. Right? It might be a board that goes into different computer manufacturers' computers. Right? So it's got to be able to be compatible with whatever they have in their systems. So it's called interoperability. It's got to go in anything and work. So the way to do that is to apply standard to that. For example, if it's a communications pathway, apply standard to that, and so you have to test it to this specification. So we know if you put it anywhere in any box, it's going to work the first time. So we have it's called compliance. We have compliance systems to be able to test that to a specific standard. That's really important, interoperability. And there's a lot, even within a controller, there's a lot of signals going around, and they can interfere with things. And you might have, you might buy this from this manufacturer of this whole board. You might buy this wireless module from another manufacturer of wireless modules, or two manufacturers of wireless modules. When you plug it in, you have to make sure it works. You have no control over this, but you have to make sure it works right out of the box, and they have to make sure that it works to a certain standard before they even send it to you. So there's several layers of this, and testing on every level, and that's sort of where we feed it. I have a couple of pieces here. This is a spectrum analyzer that I have here. I have a picture here. And it's actually monitoring the wireless activity in the room. Okay. So this is Wi-Fi. And if I turn on my Bluetooth, you see some other signals popping up.
And what assumes the green is the pizza? Maybe it's a microwave.
You see the spikes there, that's my Bluetooth going up, pinging the network, looking for something to connect to, right? So it's capturing all that stuff like that. So you can see there's a lot of noise in the room, right? So when you have a device, this is actually measuring with this antenna that noise in the room, as well as the Wi-Fi coming out of the Wi-Fi connection. That's that main. I think that was a microwave. Is there a microwave near here?
Nearby.
Yeah. So this will pick up microwave. Somebody is having lunch. And that's the microwave.
I'm not cooking.
That's the microwave going. Yeah. This is the perfect time to do it. I like doing these during lunch and learns. The reason I have two screens here is just where our technology differs from most manufacturers. This is a typical spectrum analysis trace that you find with traditional. Do you have any spectrum analyzers upstairs? Anywhere?
Yeah.
You do? Yeah. This is a typical. Do you know which one you have? Is it a HP or a Keysight? Well, anyways, it probably looks similar to this, right? We call a swept spectrum analysis, where we give you tens of thousands of spectrums a second to be able to see signals within signals.
So what frequency ranges are we looking at?
This is 2.4, 2.5 gigahertz. What is a
Is there interference from the electronics and motors and stuff?
Those are typically lower bandwidth. Typically, it's going to be your microwave and any other Wi-Fi. Anyone turning on their Bluetooth in the area. Bluetooth and Wi-Fi are typically, maybe some Zigbee are in there as well. But this profile here is a typical Wi-Fi. It's kind of neat. Yeah, so wondering if the IoT device is transmitting, we have a whole host of products to do that. This is a really important thing to do because more and more wireless devices, wireless modules are being integrated with everything in your home, for example. So architecture, wireless modules are getting smaller and smaller and smaller, so they have to be run by smaller and smaller batteries. As you can see, hearing aids to even contact lenses. It's pretty crazy. Flexible electronics, rings that can sense your bodily functions. So you have to pack in a lot of stuff in there and have it run by a small battery and connect to the outside world in a powerful enough method. So there's a lot going on. This is your thermostat there. So I keep harping on this power consumption because batteries are getting smaller, the devices need to draw less power, so to be able to measure that is really important in IoT devices. Right, so any of your projects upstairs in STEM core, if you're using a battery, to really understand how your device performs under battery, not only at full charge, but as the battery charges down, how is your device going to perform? That's really important. As well as if it's hot out or cold out. The battery profile, if you will, output profile is going to change. So you have to be able to put, and that's where the simulator comes in, battery simulator. You can actually simulate any type of battery and under any condition and make sure that your device that you're building can perform at those different levels of power output in the battery. That's sort of what this is talking about. Some more power consumption under different states. We can actually measure that and give you sort of a trace of what it looks like, the output of the power device. And then we have a whole host of products to do that, from BMMs and power battery simulators and source meters. EMC, EMI. So maybe you've learned in your courses something called In mechanics, it's resonance, right? You have all these resonances. In electronics, it's EMI, electromechanical interference. So if you have a device, it could be disturbed by other electronic devices in the area, right? So if they're emitting like crazy, it can mess up your device. So you have to either do shielding around it or make sure it's not emitting too much. So there's very specific standards to that. You'll be able to measure that at for specific frequencies, like this. There's a body, a governing body that says you can't, if you're, like in Europe has a bit different standard than the US. They may give you sort of a profile saying you can't have noise above this value at these frequencies. So these are frequencies. Right? So if you have a spike somewhere, that product is going to fail. You design it, build it into your box. Typically you send it to an outside house to test to make sure that it passes. And if it doesn't pass, it goes back to your lab and you got to figure out what's wrong. So that's where some of these come in handy. You can actually measure and see what's happening with your device, where it's emitting, where it's skewing noise, if you will. So this is really important. And this is sort of, you design it, you send it out to a outside place. They can test it, they say it passes or fails, and then it goes back to design. You got to figure out what's wrong with it, goes back and forth. This is a $10,000 a day situation in these companies. So it's really important that they design it right the first time. So it's really, it's dollars and cents for companies. When you get out there, this is a really important subject. This just talks about the how Wi-Fi, there's very specific standards that they're pushing more and more. They're upping the bandwidth of them, the speed, capacity, and you have to be able to test these. So this is that RSA 306, which I talked about here. You can do all that, do all those measurements. And this is a list price is a $4,000 box, which is a pretty low cost. With education, it's much lower. So we've actually worked with Queens Community College. I don't know if you've talked to those guys over there. So they put together an RF lab consisting of a scope or a whole test setup. So a scope like this, a DMM, a spectrum analyzer, a spectrum network analyzer to be able to learn how to test these wireless devices, mainly for the communication industry, to prepare their students for jobs for like Nokia, Cisco, and places like that. So it's come in handy at that institution. This just sort of mimics what I just showed you. When you have the Wi-Fi devices with Bluetooth, you might have like a microwave oven. This is a microwave oven, your Wi-Fi signal, Bluetooth. There's a lot of signals out there that have to be survive in the world and be able to communicate effectively. I wanted to go into probably the most popular piece of test gear for electrical engineers in the field. Once you get in the field, is an oscilloscope. Right. So I know you have a bunch here. How many here have used them upstairs? Anybody? No, of course. So what does an oscilloscope do? So this is going to be quickly go through what an oscilloscope does, because it's a pretty basic and fundamental testing tool that's you're going to find when you get out into the real world. Typically, we're going to focus on AC, so alternating signals. Okay? This is a picture of our founders, Tektronix, back in the 50s. That's the first oscilloscope. So this oscilloscope now looks like this. And this is a space heater, by the way. This thing could heat a room. It was a lot of power to run that thing.
I think we have one of those
Oh, do you?
That's the new one.
in Josh's lab. Had one of those.
And that was the screen.
That's the new one.
So, yeah, so oscilloscopes are needed and used all the time for from the original space programs, telecommunications, entertainment, radar, and avionics, medical instrumentation, anything with an AC signal. So we sort of updated these scopes. Now they're touchscreen, so I can move this signal. It's like using an iPhone, color displays. It's pretty handy. And this one actually we've integrated a spectrum analyzer into it as well as a function generator all in that one box. So it's like a lab on a bench, lab in a box. So basically you're visualizing alternating current signals in your device. And these signals can be, in communication, is 10 gigahertz or more. We have oscilloscopes. This happens to be a 1 gigahertz oscilloscope. We have oscilloscopes that go up to 70 gigahertz. So you can measure a 70 gigahertz alternating signal. So it could be radar, computers, displays, power, even if it's power 60 hertz. It's really important to be able to measure it and for testing efficiencies of power, to actually see that. Those waveforms are really important. Especially if you're building power electronics that are going to power other pieces of equipment. You're just selling power electronics to people who build it into their equipment. They have to know that it's going to be clean power. There isn't going to be any noise on that power, even though it's 60 hertz, which seems, tens of hertz. It's pretty low. They need to know it's really clean and really efficient. Oscilloscopes help them do that. And those waves could be, they can look at any of these forms: sawtooth, triangle wave, rectangular wave. So you just need a fast enough oscilloscope to be able to measure whatever you need to measure any periodic wave. It could be complex as well. A lot of times in communications, these complex waves equate to communication words. Right? When there's communication inside this box from chip to chip, for example, or Wi-Fi, you're communicating using Wi-Fi. It's actually, there's a language that allows it to communicate between one place and another, whether it be in a box of electronics or over the air. So you build in this communication. You have to be able, sometimes, a lot of times, we can decode that information using an oscilloscope. You want to make sure that your communication in your device that you're building is communicating properly. So if it has to communicate with the outside world a lot of times, you have to know that communication, that you're speaking the same language. And you're not mumbling your words, if you will. We can actually see that you're mumbling your words with the oscilloscope. So it just shows, basically this is voltage. It just shows the signal changing over time, right? And there's various components in how it works, right? So you have the signal comes in, it gets amplified, goes in an analog to digital converter, goes into memory, you process it, goes into memory, and then it goes on the display. So there's a lot of electronics between the input and the display. That's a typical makeup of an oscilloscope. And there's things that if you were in the market for an oscilloscope, so when you get out into the real world, you have a project, you have to figure out, okay, what kind of oscilloscope do I need to get to be able to test this product that I'm working with, right? And there's various parameters. There's a bandwidth, so basically how fast the signal it is. That may not be an issue. Maybe I just need to be able to measure that the signal rises in a nanosecond. I don't care how often it occurs. I need to be able to measure that curve, so to speak, the gradient of that curve of voltage swing. That's where that rise time comes in, be able to measure a rise time. Sample rate. Since it's a digital system, it's taking samples. It's measuring that curve. It's splitting up that curve into samples. So how many samples do you really need to know how fast that signal is moving, right? 3, 4, 5, 6. You need to know how many samples you need to take to be able to extrapolate that line, right? Put that line together. That's really important. And that's what the sample rate comes in.
Do these key parameters affect the price, I assume?
Yes. Yes. So this is, this device is roughly 3 gigasample per second, so it can take 3 gigasamples in 1 second. We have other boxes that take 200 gigasamples per second. That's that 70 gigahertz. So there's a lot of science and technology to be able to give you an accurate representation of your signal in an oscilloscope. So that goes with the cost of the oscilloscope. Record length is really important. So your device puts out a lot of information, a lot of signals. You want to be able to capture all those signals, especially if it's a communications device. You want to hear it talk for a long time and then see if it was speaking the right language the whole time. That's where the record length comes in. So we could capture, and that's the whole record, right? This is I'm capturing all these signals. Right? I'm capturing all these signals, and then I'll be able to analyze those later. That's where record length comes in. So those are 4 key things for an oscilloscope. Any kind of oscilloscope you buy, you're going to need to know if all those things work. The main one is bandwidth. Bandwidth means, say you have a, we call it a function generator, but say you have something that puts out a sine wave, and you start turning up the frequency of that sine wave, right? 100 hertz, 200 hertz, 300 hertz. What's going to happen is the oscilloscope is going to be able to read that up to a certain point. And when that certain point is 30% down from its peak, right, it's not going to be able to measure it. Say you put in, say the oscilloscope is a 200 megahertz oscilloscope. If you put in a 200 megahertz signal, at 200 megahertz, the amplitude of that signal is going to go down 30%. That's how we specify how fast of a scope it is. That's sort of we call it 3 dB down. That's how it's specified. So that's just something that is known in the industry. Also, there's a bit more than that. So you want an oscilloscope that can measure more than faster than the signal you want it to be trying to measure, right? So if you're trying to measure a 100 megahertz signal, you don't want a 100 megahertz scope, because that 100 megahertz signal is made up of faster frequencies, more frequencies, right? So this is sort of representation of that. So you want to be able 5 times faster. You want the scope to be able to measure a signal 5 times faster than the signal that you're trying to measure, so that you've got an accurate representation of that signal. Okay? That way you're not getting into the 30% down business at frequency of interest, things like that. So that's sort of a rule of thumb. And this sort of illustrates that. If you have a high-speed signal, this is what it's going to look like if you have an oscilloscope that's 5 times that speed. If the oscilloscope is sort of equal to that, this is the way it's going to look like. It's not a true representation of your signal. And that's sort of a real world, what you're going to see if the oscilloscope isn't fast enough for the signal you're trying to measure. Is that clear? That makes sense? Feel free to ask any questions. Rise time. So that goes back to, say you're not interested in frequency, you're interested in, I want to be able to measure how fast of a signal, accuracy, how fast my signal rises accurately. And it's sort of the same general rule. You want it 5 times faster than you're trying to measure, to be able to measure that. Sample rate, that just tells you how many points, right? You have to decide how many points, and we typically 2.5 times to 10 times the fastest frequency. It sort of gives you enough points to be able to represent that curve. Right? And then record length. They're sort of hand in hand how record length and sample rate work. So it's just another parameter we need to worry about. So there's various controls on an oscilloscope, right? So vertical, obviously, you want to be able to see the whole signal, whether it's touch screen or not. And then also horizontal, which tells you to be able to put how many instances of that wave in the screen at once. Or if you want to capture a very large portion or a very small portion on the screen, you have control of it. That's what all these knobs are. So we've replaced that with touch screen, but we also still give you knobs here to control. Typically it's 4 channels, so 4 different signals can be measured at once in the oscilloscope. So this is sort of an older scope actually. This is we call our lunchbox size oscilloscope. So a lot of these for education. I don't know, what do you have?
PBS.
1,000 or 2,000?
I think PBS 1,000.
1,000, yes. It's similar to this. You have similar to this. So here you have controls. We sort of redesigned it with that one, but you have controls for each channel, amplitude, and then this is the time for that. And there's a lot of information on the screen that tells you what's happening and what it's set to. For that, controls. That. Okay, triggering. What does it mean to trigger, right? So you can have a complex signal coming into the oscilloscope. You can consider this is sort of a dumb device. It's just going to display whatever that signal is on the oscilloscope. But where are you going to take that picture of that signal? Right? It's where you take that snapshot. You can set up the scope to say, okay, I've had it set up here, if you can see from back there. I have many of the same signals on my input, but once in a while I have what's called a runt. It doesn't quite go all the way up to the top, but it's still there, somewhere in between the 0 and whatever 3 or 4 volts that it is. That's called a runt. So I've set up the oscilloscopes to take a picture of your signal at that runt. So that's what trigger means. You can set it up to just capture at every edge, right? So at the middle of the screen is going to be on one of the edges. You can have it set up at something like a runt, or you can have it set up, see there's a narrower pulse here. You can say, okay, trigger on the scope when that pulse is less than 10 nanoseconds, or what have you, right? So you can tell, that's what trigger means. Trigger is take a snapshot of my signal. How are we doing? Oh, we're getting close. Take a snap of my signal, and this is how I want you to take a snap of my signal when it's set up like this part of my signal, right? And a lot of times you don't know what you're looking for, so you just have to be able to capture and then search through to see if there's any anomalies, because these are anomalies. Captured. What's nice is on a lot of these oscilloscopes there's an auto set. So I can just hit auto set, and then it automatically captures. It picks what's called an edge trigger, just looking for a rise time, and then triggers the scope. So it's an easy way to start out your scope. Sometimes on the education scopes, the professors will turn that off. It forces you to set the scope up to be able to trigger on the signal of interest. So we allow them to do that. We allow them to turn off that trigger with an auto set functionality. So what can you do with an oscilloscope? Okay, now I've captured the wave. Okay, what do I want to do with it? What do I need to know about my wave? This is where you can make measurements. Okay, so you can actually measure a lot of things. The minimum signal, the maximum signal, how fast it's rising, the pulse width. I want to know how that's really important to a lot of these engineers. They want to know how wide those pulses are. They have to be a certain width. Peak to peak. If say it's positive and negative, they want to know how large that peak to peak is. Delay from pulse to pulse. That signal might not be exactly at every 10 nanoseconds. It might be 9 nanoseconds, then 11, and then 2. They want to be able to measure that. That's what the delay is. There's a whole host. There's a lot of other measurements they can do. And especially like for power, we have a host of measurements for power because there's a whole language of measuring power. Devices that put out electronic power for other reasons. So you need to measure all these different parameters on that. So that's all could be built into the oscilloscope. What's nice is it's, there's a built-in computer, so the computer can do whatever you program it to do, right? So it can measure all these things. Once you've gotten the signal in, you digitize it, you let those ones and zeros in the scope, you can just apply math to it and be able to measure all these things. So it's a really powerful tool. And that's why it's used so heavily in your electronic degree. Yeah, so this is sort of a high-level view of what you can do with an oscilloscope. So serial bus. So that's sort of a serial communication. So people, they develop or they use serial communication in their devices. So you can send that electronic signal into the oscilloscope and actually decode that language. You can translate that language into words. And that's what this is doing here. And so it's taking all that gibberish and actually giving you some code what that all means. This all means something. I can tell you what that is. And as an engineer, you know what those words should be. So if you see something, you'll know there's an error. Power, that's just, I would measure power, that's sort of a one screen you can use. Jitter is sort of that, I was telling you, if the signal isn't coming at the right regular intervals, we call that jitter. Sometimes it's before and after, and the more jitter there is in the signal, this is what you see here is like it's taking every signal and overlaying on top of each other. So you can actually see where there's jitter. If there wasn't any jitter, you would just see every line on top of each other. But here, some come earlier, some come later, and you can actually see that. And there are actually parameters for that in a lot of these communication systems. Then you can have this amount of jitter. They can still work with a certain amount of jitter, and they're specified that way. And as long as you can measure and you stay within those bounds, you know the product will work. RF, I don't know if I have time to get into RF, but radio frequency, you're basically measuring the frequencies of your electronic signals, like the spectrum analyzer here, which I showed you. It's measuring the frequencies. Yep, that's pretty much it in there. Any questions on oscilloscope? Let me pull up one other unique thing that we've done with DMMs. So the DMM is probably the second most popular tool for an electronic engineer. So what a DMM does is it measures, if an oscilloscope measures an AC signal, alternating current, a DMM is mainly designed for DC, direct current, right? So it's measuring just sort of a level of voltage. You want to measure a voltage, you want to measure a current, you want to measure resistance. You may want to measure resistance in your device. That's really important to do. Make sure there isn't too much or too little resistance. So those can all be controlled with the front panel. I have one over here. DMM. So you can choose your measurement. So literally, it's a touch screen. You say I want to measure DC current, DC voltage. We've actually built in sort of a quasi oscilloscope feature in there, where actually you can measure. You can think of it as like a 1 or 10 kilohertz oscilloscope. So even if your signal is varying a little bit, we can capture it with that.
Yes.
But typically, it's measuring just direct signals. So we've actually translated that touchscreen technology into DMM.
So is DMM just digital multimeter?
Yeah, digital multimeter. Yeah, sorry. Yeah, and they use that, and then you can. When I was talking about long-term testing, temperature testing, typically what customers will do is connect up a DMM. This is a data acquisition. Basically, all that means is a DMM that can measure 80 channels, right? At the back of it, you'll have 80 channels coming out of it to be able to measure, say you're making a device, you want to put 80 of these in a temperature chamber, which is very often done. to cycle the temperature of that device and then measure its performance over 24 hours. Or I have a customer, it takes them 3 weeks to test one device, because they're testing for a lot of different parameters. And it's going in a satellite, so they have to make sure it's pressure, temperature, vibration, everything is tested. It takes 3 weeks. And they have to make sure that there are any breaks in that testing. It's got to be continuous. The government dictates that. It's a lot of fun. Anyway.
Sam, so we have 5 minutes. I know some people do have to
Yeah,
leave
yeah,
at
yeah.
1:30. And they're going to stick around. Sam and Scott, I'm going to stick around for maybe about half an hour
Yeah, yeah.
for you guys to play around with the equipment. For those of you who have to leave, if you have any questions, can you tell us a little bit about the bigger oscilloscope that you brought that is a multifunction, and what are some of the specs that will have versus a regular oscilloscope?
Mm-hmm.
And us as an educational institution, what's the benefit of having something like this? Can we perhaps showcase that screen into the screen and then let the students see what's going on, rather than have everyone around the room looking at the same screen, things like that. Like,
Sure.
Yeah, as Sam sets that up, one of the key things, and just to reiterate what Sam mentioned at the beginning of the whole seminar here, it's, first, we've seen many schools, and very few have the equipment that you have here. And the real key here is the objective to give you the skills to go into the real world. And just that you saw a variety of applications that these instruments give you the skills to work with. And it goes from medical commercial, to just military, just all kinds of different areas. And if you have the skills to work with the instrument, so many job openings are out there. And we've seen a number of schools that teach how these instruments work. And you're a technician, you walk out of here, and that's an extremely valuable skill. Then, as you go further into study, it's going to get more into the theory, put the two together, and you've got a real strong background.
I'm one of the counselors here for our semesters, so are there things you recommend outside of the academics in the school that students can be doing to help make them more employable when they do finish their studies?
This is ideal, getting the hands-on work, how these instruments function. We were just talking earlier, if you look up RF engineer within a 10-mile radius, and you'll see so many job openings. It's everything, just as Sam said, your refrigerator's connected, your car, fobs, anything is RF, radio frequency connected. And to have the skills to create and design instruments that fall within that field and allow you to design the circuitry. We had one incident where it was a military application where they're trying to determine these roadside explosives. Well, you have to have a function generator, a device that creates that signal, and then you devise or design a product that can sense that signal. So that you're looking at both ends of what's going on. So then you take that into operating your refrigerator remotely, your Nest, front doorbell, all of these things here. Now they have light bulbs, smart light bulbs. I've never seen a smart contact lens. That's a cool one. That, who's watching you, what you're watching, I don't know. But you just see how, the key here is you have the skills to take into a multiple number of fields.
So much of that real world exposure that
Exactly,
you get just
exactly,
immersed
yeah.
in that.
And you can then plug yourself in
And
to
YouTube.
many openings.
YouTube is huge. We have an application engineer. His name is Alan Wilkie. He's based in New Jersey. He has a YouTube channel. I can give you his the name of his YouTube channel, and he's had 10 million views of his site. And he has a whole host of videos on basic electronic measurement concepts. He's really good. He actually makes money on his YouTube. Not as much as Tektronix, but he makes.
Billionth of a cent, I think, each video is.
Right,
is that a technical question about?
Can I ask a question about can this detect multiple different inputs simultaneously? Because you said earlier it can detect same input 24, but we would like to use different input like voltage, current, temperature, all the inputs simultaneously. Can it do that?
Yes.
Okay.
So, will it? It's what it's going to do. If it's the DMM.
But I see only one input.
Yeah, on the back.
Back has a
Like
different
for example,
input
this one you can get a 10 channel
or 10 channel
And
output.
this is the
input,
DMM
right?
here.
Okay.
You get a 10-channel card and it'll scan
Or
10
that will
channels.
come with this one, we have to buy that separately?
Yeah, it's an option.
So that extra added value then,
Sorry?
extra value then.
Extra value. And then there's a version of this that you can do 100 channels of that. And all different, temperature, current, voltage. So here's we call our MDO3. So we've integrated the oscilloscope functionality. We have a function generator. We have a spectrum analyzer in here as well. There's a digital voltmeter, you can measure voltage. You can have analog and digital. And so we sort of integrated everything, and this goes much higher bandwidth than what you have, but what's nice about this one is it starts at 100 megahertz. I think the one you have is probably 70 megahertz. You have 100 megahertz? Okay. So this one, as the model starts at 100 megahertz, but you can upgrade it in the field with just the key code. So if you have, you sort of grow with it, right? It's good for what you're doing now, but say you have other projects, instead of buying a whole new scope, you just upgrade this as sort of investment protection. Anything, any aspect of this scope, other than the number of channels, because it comes in either 2 or 4 channels, you can upgrade. So if you're doing work in serial decoding, you can add a serial decode package later. If you're doing power, you can add a power package later. You can add the digital channels here. So everything's included in the scope, and then you can upgrade it later if you need. Only buy what you need. So it's a good way of controlling costs, having costs attached to a project.
So talking about cost, and I don't want to put you in the spot, but educational price for a 100 megahertz 4-channel device like that, ballpark, what is it?
Between 3,000 and 4,000.
Okay.
Well, there's educational price and there's the lease price.
You know that you know. Okay, good to know.
So we've sold a lot of these. We just helped out Temple University. They have a makerspace that's almost as good as yours, almost. But they purchased, I think, 9 of these for that. They have scopes, they have DMMs, function generators, and then a couple of higher-end oscilloscopes for projects, senior projects and things like that.
So I have a question for the students. Why do you think these companies have such deep educational discounts? Everybody put 2 and 2 together to think about what they're investing in?
Their workforce is declining, so they need younger blood.
Okay. Anybody else? Someday, you're gonna be the decision maker. So you're gonna sit here, you're gonna grow up in school, and then your first job, and you're gonna kind of get used to Tektronix logic and be a sort of a Tektronix person. Don't you think when you're in charge of buying the next set of oscilloscopes, who are you gonna call first? HP or Tektronix? You're gonna call Tektronix because you're sort of gotten used to that, you've become under their, it's not a spell, it's a good spell, but that's exactly what they're investing in. They're investing in you as
Yeah.
students. They're not just trying to sell it to Bergen Community College. They're trying to sell equipment to you 15 years from now when you're the decision makers. So it's a culture, right? It's a Tektronix culture. So the companies are really, you're their investment. It's the students who are going to become the future engineers.
Hey, do you want a job? No, he's right. He's exactly right. I mean, and it's more than just an educational discount. So we've done things like you buy a certain amount and we donate some, charitable contributions. I mean, the Temple is a perfect example. We donated $30,000 worth of equipment because they spent a whole bunch of money, and then we donated $30,000 because not only it benefits what you're doing now, but it opens up possibilities on what other things you can do because you have the equipment, right? It doesn't help us if no one buys it and no one uses it, right? It helps. We'd rather you use something and come up with ideas for other things you can use it, right? It sort of expands your possibilities, right? That's basically what it comes down to. So this is just, we've built in, for the latest generation, all touch screen controls.
All students now, everything is screen. Automatic.
I was at UPenn, University of Pennsylvania, and they have a lab where they use a separate function generator to generate a sine wave, for example. Students preferred to use the app on their phone to generate the sine wave because it was easier to use than this box on the bench. Right? It's just sort of so we're trying to keep up with that. Right? Not only technology is changing, but how to use the technology is changing. And we have to keep up with it. For example, the spectrum analyzer. Historically, spectrum analyzers had a computer built in. Right? We've gone to what's called a disaggregated model, where you can use your latest computer to control the spectrum analyzer. Spectrum analyzer just spits out IQ data, right? Your computer can do all the analysis. Why should we lock up that performance in the instrument itself? And as computers develop, we've just handcuffed you on what you can do with spectrum analyzer. So that's something we've done with spectrum analyzer, and we have to do that with scopes. Like this scope we sort of future-proofed it. We've built a lot more capability into the scope than we've actually unlocked, right, with this design and all of our latest designs, so that we can add features to it without bogging down the oscilloscope. It's something we thought ahead. It's just a whole new hardware front end on these scopes to be able to, as things move, larger memories, faster bandwidth, right?
Yeah, and also to piggyback on Dr. Ricardo's comment, for you guys, for you students, when you start applying to jobs and internships, if you mention that you have skills utilizing these equipment, that makes you very appealing to employers. Like, not everyone comes out of a community college knowing how to use oscilloscope, a signal generator, a frequency analyzer. So this is powerful skills for you guys to potentially add to your resume, and if not, to mention it during your interview. I am proficient utilizing electronic equipment, and that makes you a lot more attractive to these potential employers. So by all means, this is a great investment. Thank you guys for coming.
Yeah, thanks for having us. Any other questions?
So since you said it's like a language, I believe the different shape has different meaning, like on the graph.
Right. So it's typically the patterns of the peaks.
Yes.
It creates the pattern. It creates the language. Right. So there's like sort of a language saying, okay, if you have so many peaks in so of this width in this much amount of time, that means something, right? And a lot of times it could be not just one connection; it could be two connections. So there's signals on both, and they're sort of matched to each other. And you say, okay, you're sending this on this line and this on this line, and with the two of them, you have a language. And sometimes it's four. It could be 4 lines of signals that make up one language. So there's a lot of different things.
Wow, that's hard to apply.
It can get once you get the initial concept, the rest sort of comes after that.
So I remember like that is shaped a little more like rectangular, but there was like something like more circle. So can you explain me how are they different? What's the meaning of that?
Sure. So typically in communications, it's going to be more like this, more square wave,
Yeah.
right? Because it's not. They want because they want it to be very clear what it is.
Mm-hmm.
Sort of a sine wave isn't very clear on what it is.
Mm-hmm.
They want very discrete peaks. That's why you need an oscilloscope that can actually see that square wave accurately. Right? So they know it gives you better definition. It's a very clear language. The sine wave, it's too messy to. At lower speeds, it's very messy. And it's really hard to communicate with sine waves. You need to have very discrete signals. I can probably show you a.
That's why they go to a digital signal.
Mm-hmm.
Digital signal, you can see like a 1 or a 0.
Mm-hmm.
And sine wave, maybe it's going to drop, it's going to move, it's going to rise. Here you know exactly what that signal is. And the scope, the better scopes, break that signal into multiple components. So when Sam mentions the number of samples, you're looking at millions of samples per second. You're getting a very, very good look at what that individual signal looks like. So it's not going to be jagged. You're going to really get it. You're really cutting it up so well to get exactly what that signal looks like. And in effect, you're almost building a sine wave by all those little digital signals that you're getting.
They can also like, there would be something like so rectangular is the most interesting.
Right.
And what about the triangle?
So the machine also is capable of doing little different signals. So, such as a signal generator. So there's one. What's the one they call the heart rate? You know, the heart rate monitor.
So here is this is what's called RS-232. That's a serial standard, which is in a lot of computers. That's probably the oldest communication port at the back of a computer is an RS-232 signal. And zoom in
I
more.
see that that's really good information, very accurate.
Right, so here, this is a piece of information. It means 78, right? This means 69. You can see how it varies, differs. If those were sine waves, it'd be very difficult to be able to read what that was. See how narrow they are? So the spacing, the number of pulses, the spacing of the pulses, the height of the pulses, all of that equates to 69. And all this equates to 78. So that just tells you why a sine wave would be very difficult to translate that. So serial communications is try to make them square.
Then the 21 is more wider, the most wider thing, but that's 20. So where is the number from?
Oh, it's just a computer code.
Okay.
The 20 is just a computer code. The computer knows what that means. I don't know what it means, but the computer knows what that means. I think I have
They call it the protocol analysis.
Here,
Identifying portions of the signal.
there we go. I just translated it.
Oh, I see.
That's an I, this is an X, it's a period.
Okay, so that's kind of neat.
Yeah, so we actually,
That's the code for buy Tektronix.
there is, no, it does say something like
If we
that.
move on to the next line, it says at a discount.
They're like steep discount.
Right, guys, any more questions specific to the equipment that we have here?
Yes, that's Tektronix.
Tektronix, there you go. Applications, things that you wonder if you can use that for X and Y.
What was that YouTube channel, Alex?
No, Alan Wilkie, I have his card.
We'll get you his address.
Okay.
I think I gave it to you last time.
Perhaps, yeah.
I did.
I don't know, if you have it again, you know, I will take it,
Yeah, it was called.
and I'll share that with you guys.
Yes, here's, you can write it,
Is that
come up
the
here and
one
write it
that-
down. Huh?
Okay, yeah, I remember that one. There was
But
a
if you
picture
want to write it
of
down, his YouTube channel is W2AEW.
I'll write it up for you.
W2AEW. AEW.
That's his ham radio.
That's his ham radio, sorry, he's a ham.
The spectrum analyzer, how does it interface with the computer? Are we talking USB or what's it?
Yeah, this particular one is USB 3.
Okay.
So this is pretty unique. This is, it gets all its power and control with USB 3.
Okay.
So you don't have to
And
plug
does
it into the
use
wall.
proprietary software on the host PC, or is it something that?
It's on the host PC.
Okay. Have you considered using some type of mobile interface with it, or is the power demand too high?
Power demand is too high, yeah. You need, because it's powered from the computer. We have other ones you can plug into the wall, and or in other ways that have their own battery, larger ones.
We've got a catalog.
So the larger one is about this big,
This is huge.
has a battery built in. I recommend checking out Alan's website, YouTube channel. He's pretty amazing. So it's like, he says the most popular. He always tells a story. Alan says the most popular video he made, had the most hits initially, was how to coil up an extension cord properly, so that you can coil it up and then just throw it out and it will unravel without getting tangled. That was one of the most popular videos.
Small things in life.
Yeah, it's pretty fun. He's an asset. He's local, so he would be your support
Nice.
for equipment.
Guys, any other questions? Yes,
Wait,
yeah.
I have one more question. So is the device work as a reader or like actually it can give an order?
The oscilloscope, mainly reader, it's just gonna take in information and decode it. But there is something called a function generator in the back that spits out an electronic signal. So if you need to create an electronic signal,
Like a function?
like a function, yeah, like a function, it could be a sine wave, square wave, sawtooth wave, you can do that with there's an output in the back that can do that.
Thank you.
Yep.
Anything else?
Good, bad, criticisms, I could take it,
That's interesting.
yeah, makes sense.
How many of those can you leave behind?
I don't know if it was helpful, I can leave one here for a week or two if you feel it would be used in,
Well, right now it's a peak time for us, we have
yeah,
a lot going on.
well, not right now, but in general,
Yeah, okay.
You know, if you had, if you had sort of a
Perhaps during the
workshop,
winter break, that might
Did a
be a good
workshop
time for
or
us to play
something.
around with it, yeah. Okay, anything else? All right, well, thank you very much.
thanks guys. Appreciate it.